All right, hopefully you guys have just had a very successful quiz experience. I will get those graded soon. You won't get them back till after Thanksgiving break, though, uh, because we'll be out of town and then we have break, and I don't have any way to get them back to you. So I'll get them graded as soon as I can, and we'll get to work. You guys should be getting your lab reports back as well today, and those grades should be in there, and we'll continue to work on that. Generally speaking, they were pretty good. We're going to do some stuff though to work on science reasoning, because that's really what I think the main benefit of lab reports are, really to get you to look at evidence and draw conclusions, and that's where, generally speaking, most of y'all are struggling the most. So, in conjunction with continuing to do labs, we're going to do some science reasoning type stuff so that you guys can really come out of this class improved in that. All right, on to the lesson today, which is a very important topic: Lewis structures. Let's see how that's looking up there. All right, actually looks pretty good. Okay, so up until now we've been talking about bonding, okay, and we talked about ionic bonds, okay, and that of course is the transfer of electrons. Okay, but now we want to move on from just ionic bonds, which are really just between, 1, 2, or 3 electrically charged elements, okay, or atoms, electrically charged atoms, ions, that really limits us to what we can talk about, because many, many more compounds are covalently bonded. And the only way that we can talk about those is following some rules to draw what they look like. And to me, this is pretty satisfying, because we're really getting into what do these things actually look like. Okay? So go ahead and flip. I think just doing these and following the rules is the best way to do it. All right? So we're literally just going to follow the direction of the chapter here, and then we're going to talk more in depth about some of these. All right, so flip over to page 136. All right, and I'm not exactly sure how much of this we covered the other day, but I'm just going to take us back because we've got to slow some of this down anyway. So this is a good opportunity, if I've gone over this, to go over it again. Oh, and about naming. I am still beginning to draw conclusions about what we need to do for this, because just honestly, I was not taught very well this, and so I just was told to memorize them, and I don't want to ask you guys to do that. And I said this in the other video. I think we are just going to have to do some memorizing, but I'm and you guys help me, think through this. Like, is this helpful to try and memorize, or is that rule itself so difficult to memorize that it's better just to, pound it out with note cards, and you flip them back and forth and make a Quizlet and this and that and the other until you just can pass a quiz on it. And this guy is all about not doing the cram and forget thing, but at the same time, like, are you ever going to know these really well enough that you're going to be able to use them fluidly and not just look them up? And, I guess I'm just trying to balance you guys' mental resources and how much time to get you to put into this with the usefulness of that. And I'm just still really undecided about that. I'm certainly going to give you guys an answer, this week or sometime over the break, so you know what you've got to study for. And I'm sorry I'm so indecisive about it. I don't have a good answer, and my own chemistry education is so not great, that I don't know what the right thing to do is there. So I'll let you guys know about that. I'm sorry to be indecisive. I'm sorry it's confusing to you. I'm working through it in my mind, and you guys are just going to have to live with me doing that. I'll let you know something as soon as I can. All right. So, but on to something way more concrete and way more thoughtful rather than just memorizing is Lewis structures. All right. So what we've got here is we've got shared pairs of electrons. All right. So whereas before we were talking about ionic bonds, they're transferring the electrons. You come to covalent, and now we're sharing. Okay. So we've got the transfer here, and then we've got the covalent, and that's the shared. Okay, so how do they share? Well, I'm glad you guys asked. All right, so right here on 136, we've got the bonding pairs, and we replace those with a line. And then we have the non-bonding pairs, and we only do those on the central atom of the molecule. Okay, so this is going to be a lesson full of rules, but rules that are very reflective of sort of a deep structure of nature, and so in my mind are not so terrible to deal with. All right. So one is that shared pair of electrons is represented by a line. Okay. And then non-bonding pairs, they are drawn only on central atom. Okay? All right. So let's just jump right into it, okay? So we've got, on the next page, we're going to do CH4. What is that? That's methane. Okay? And if you look really fast, this can help you when we're going to need to know things. Methyl group is not actually on here. Okay, never mind. Scratch that. I was going to draw a conclusion that is not actually in this chapter. So forget that. All right, so methane, CH4, it is the simplest of the hydrocarbons. So you've got like butane, octane, all those anes that you know about. Methane is the simplest one. It's only got one C. All right. Then we got phosphorus trichloride, and sulfur dioxide, and boron trifluoride. Okay. All right. So what do we do? We're going to look at our rules to see which ones apply. Flip over to the next page, page 138. All right, let's read through these rules together before we start drawing any of these, okay? All right, write down the chemical symbols for the atoms of the molecule. We did that. If there are more than two, then one of them is in the center. Okay, so we are still in the 2 right here. Okay, so so no, we're not in the 2 because we've actually got more than, so this has got 5 right here. 4, 3, 4. Okay, so one of these and all of these has got to be in the center, right? If the molecule contains one of one kind of atom and 2 or more of a different atom, then the single one is in the center. All right, so let's apply that here. The C is the single, so it's in the center. P is in the center. S is in the center, and B is in the center. Okay, all right. Because those are the singles and there are multiples attached to them, and then they're in the center. The singles in the center, okay? Otherwise, the least electronegative element is in the center. All right, so who's never going to be in the center? Fluorine. Fluorine is the most electronegative. It is not going to be in the center. Okay? Hydrogen is never in the center. Halogens usually aren't in the center. Again, because they're pretty electronegative usually. Okay? But unless there's one of them and more than one of something else, which is not usually the case, but again, things are not always simple in chemistry. All right, so something that we might, let's continue on. I'm kind of jumping around here. I've never taught this lesson before, so sorry. All right, before we come back to this, let's continue making our rules, okay? And then we'll come back and we'll apply them. All right, so singles go in the center, okay? Like we said, we got a C, is a single, there are multiple H's, so singles go in the center. All right. Not electronegative goes in the center. Okay, so we're just pulling out of here these rules so that we can be a little bit more focused and not be trying to read whole paragraphs, okay? Hydrogen, never in the center. And why do we think that is? Why is hydrogen never in the center? Well, hydrogen's never in the center because for hydrogen to be in the center of a molecule that has two or more other atoms in it, it would have to bond with more than one. Okay, and we know that hydrogen is satisfied when it's got a full S shell, which has only got 2 electrons. And so what shell is it going to use to bond with if it can only bond with 2 electrons and be happy? Okay, so it kind of makes sense that hydrogen is never in the center. It just doesn't have enough valence electrons to go around and make it the center of attention there. All right, and I'm just going to add the so, not halogens usually, okay, along with 4. They're kind of related. Sometimes there will be a more electronegative than some of the lower halogens down here, but the halogens we're dealing with, they're not going to be in the center. All right? Now, let's look right here. Arrange the atoms around the central atom. Okay? Where did we say? Oh yeah, if carbon is present, it is the one in the center. Okay? So we'll just call that carbon is the center. Okay? That means anytime if you've got blankety blankety blank and a carbon, you know where you got to start. Carbon's going to be in the center and everything else is going to build off of that. Okay? More than one carbon and they form a carbon chain in the center. Okay, they call it the carbon backbone. Okay? All right? And that's it. All right. Now, let's go back. So we've got our rules. You guys should have these rules written down. If you guys need to talk about it, feel free to pause me. I won't even know it. Won't even hurt my feelings if you tell me you paused me. All right. So CH4. Let's bring that down here and then let's apply our rules. So we've got an easy one on this one, right? Carbon's the center. All right. So we're just going to draw our C. Okay. And now what do we need to do next? Add up all the valence electrons. Okay? Well, how do we do that? What are our valence electrons? Well, we are so familiar with them, we don't even need to look, but I'm just going to put this out here just in case. So how do we do the valence? We know 1, 2, 3, 4, 5, 6, 7, 8. So we've got C, 1, 2, 3, 4. Okay. And then H, they're in the 1, and we've got 4 of those. So 4H gives you 4. And so a total of 8 valence electrons. All right? So now what do we do? For polyatomic ions, add another electron to account for each negative charge on the molecule. We know that. Okay, or subtract one electron to the account for each positive charge on the molecule. All right, we'll do some of those just to get familiar with that in a minute. But that's not the case here. Arrange the electrons in pairs to give an octet around each of the atoms, except hydrogen, which only gets a pair. Okay, so we got 8 valence electrons. So carbon needs an octet. So we're just going to say 1, 2, 3, 4, 5, 6, 7, 8. Carbon's in the center, and we've got 4 H's, so we're just going to do this. Okay, and we're happy. Okay, why are we happy? Because carbon has got an octet. It's got 8. Hydrogen has 2, because they're sharing. They're playing nicely. They're sharing and caring. Okay? See, instead of happy trees, we have happy covalently bonded molecules. I need a big fuzzy fro like that guy. All right, so everybody's happy. And then we take out the bonds, the double electron there, the shared. Okay? And we replace it with a line. Okay? So that's it. That's a nice simple one right there. So let's look at this next one. PCl3. Okay, so first we're going to get our valence electrons. Then we're going to follow the rules to arrange. Then we're going to draw electrons to give octets. And then we're going to replace with lines. Okay, so PCl3, 1, 2, 3, 4, 5. And chlorine's got 7. So that's 21 electrons for a total of 26 electrons. Okay, so now we're going to follow the rules to arrange. Singles go in the center. Halogens don't usually, so those go together. And so I'm just going to say that that's what we got going on there. Okay, so what do we have? Let's start arranging them up. Man, I drew lines already. Sorry. Okay, let's just do this. P, Cl, Cl, Cl. Okay, so I think they're going to be arranged equally around there. All right, so what do we need to do? Let's start with the middle. We've got to get rid of 26. 1, 2, 3, 4, 5, 6. Let's just do 7, 8 and see what happens. 9, 10, 11, 12, 13, 14. And he gets to share these. 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. All right, so what's going to happen here? We've only got 3 Cl's and we've got 4 pairs of bonding electrons. We're going to get to here, and then we're going to be left with a non-bonding pair. How do we know that? Well, because the numbers don't work out for him to get bonded up. So how do we know that? Let's look. Let's draw them a little bit better. Let's do like this. So we'll do 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. Okay. So that's 26, and let's just check. We've got 8 here, 8 here, 8 here, and 8 here. Okay? So everyone's happy. And so then we replace, what are the shared ones? They're the ones that are circled by 2. So shared here, and shared here. So we're going to have P, Cl. And this one's going to remain unbonded. And we only draw the non-bonding pairs on the central atom, so we can just drop all the other ones over there. Okay? Again, this is just something you just have to practice and practice and practice and go through. All right, let's look at SO2. I just want to, y'all may already have this, and I'm sorry if I'm killing you with boredom here, but I want us to be thorough in how we learn this, so you can follow these rules when you're on your own and stuff's kind of making sense. All right, so we got SO2. Who goes in the middle? Singles go in the center, so we can just go ahead and assume it's already going to be like this. Okay. All right, then how many valence electrons do we have? 3, 4, 5, 6 for S, and 6 for the O's. Okay, so we've got 6 for this guy, 12 for the 2 O's, for a total of 18 valence electrons. And let's figure out. All right, so I'm going to draw this without those bonds. And we're going to do it. Let's put 8 around the center first and see what happens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Uh-oh. I'm out of electrons. Okay? So what do we do? What do we do when we're out of electrons? Okay? Well, the same thing you do if somebody's out of food. You share more. Okay? So what we do, actually, is we're going to take this, and I'm going to move them over to here, and I'm going to tell them to share 2 pairs of electrons on that side. Okay? So I haven't changed my number of electrons, so I got 18 electrons, but I've moved one over so that 4 electrons are shared right here, rather than just 2. And what that does is it makes them go further than they could on their own. Okay, so here's your rule. If you don't have enough electrons, when you start doing your dots, start making double bonds. Okay, that's what that represents as a double bond. And I'm going to draw this with the lines now so that that double bondness really comes home to you. Okay, so what are my shared? Here's my shared, here's my shared, and here's my shared. Okay, so I'm just going to draw that one here. O, and remember we can drop all these unshared electrons if it's not on the central. And then this over here is going to be a double bond. Okay, and we can drop these right here. Okay, but this right here, this is unshared and it's on the central one. So we're going to do that like that. Okay, that's it. All right, seems super simple, I know, and you're going to go home and you're like, wait, this wasn't like the one we did in class, okay? Just follow your rules as best you can. I'll send you guys the answers if the back of the book doesn't have them, and we'll work through it, okay? I'm not going to leave you hanging on that. All right? All right, and so the other thing that we're going to go ahead and mention right here, look on page 138. Okay, I'm going to reference right here. Okay, I want you to look at it. I can't have it on screen and show you what I got going on here. All right, so the other thing is that when you're going to talk about geometry is, look how he has this drawn. Okay, I've got mine drawn straight across. But actually, in real life, and they can measure these things with a variety of indirect techniques, okay? But in real life, this is actually much closer to what the molecules actually look like. Why is that? Well, basically, they're electrons here, electrons there, and electrons here, and they're all repelling one another because they're all negative. They're pushing away from one another. And so what it does is this set of unpaired electrons right here on that central atom forces these to bend downward to get away from the electrons that are up here. Okay, so they were like this, the extra electrons are up here, and they get pushed away until this repulsion matches this repulsion, and they settle into a stable deal. So it's like a magnet who's got north and north and north, and he's just trying to get as far away on average as he can from both of them. Okay, so we won't get super into that right now because we're going to talk a lot about that in the next chapter. But I did want you guys to be aware that that shape is changed. So be thinking about that. Okay, so that's actually, it gets bent. Okay, and the other thing is that we're going to introduce right now are called resonance structures. Okay, so what does resonance mean? All right, so if something has resonance, you guys haven't had physics yet, which is why I would love to teach physics before chemistry. All right, resonance, something resonates when it matches a particular vibration in a way that it reinforces. Okay, so any like the flute or any of the like a panpipe or even blowing on a Coke bottle, you are introducing resonance in there at a particular frequency. All right, and so it means a going back and forth. Resonating, something is going back and forth. Have you ever watched a wine glass that's about to shatter? It's vibrating back and forth a lot right before it shatters. Okay? And so what happens is we've got this S that way, and we've also got the S this way. Okay, you see how they're mirror images of one another? There is no energetically preferential, so it's not a better energy state for this atom. Remember that molecules, chemistry in general wants to minimize energy, right? So it doesn't minimize energy for it to go one way or the other. If it did, it would just settle into one of them. But basically what it does is it actually has kind of like a hybrid bond. It's like a 1.5 bond and a 1.5 bond. Okay, and we'll talk more about that as we get further into this. Okay, we've got to hurry up. We're already at half an hour here. All right, so okay, here we go. All right, so let's look at BF3. The last guy that we had. All right, very quickly, you guys want to count 1, 2, 3, and then 1, 2, 3, 4, 5, 6, 7. So 3 and 7. So we've got 3 and 3 times 7 is 21, and then equals 24 electrons. So what do we have? Single goes in the middle, and I'm just going to draw my fluorines like this, for lack of a better way to do it right now. All right, let's start dropping them in there. 1, 2, 3, 4, 5, 6, 7, 8. So it's kind of looking like maybe we're going to have an unpaired electron. We're not sure yet, okay? So it's 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay? So what's going on? This is a real compound, BF3 is, okay? And let's see, yeah. It makes sense if we were just looking at it from an ionic standpoint, because this 1, 2, 3 should be a +3. This would be a -1, and so that would seem to be the case right there. Okay, so that makes sense, but why doesn't it work right here? So what happens if we start doing the shared electrons? So we give him an octet, we give him an octet, we give him, we do a double right there to give him an octet. Okay, does that work? It does. So wait, why is this an exception? These boron with only 6 electrons. Hold on. Okay. With any other central ion except boron, that's right. When we try to form a double bond in an octet, but in boron's case, this is not energetically favorable. I'm reading from page 138 down here at the bottom. Now that there's no non-bonding pair in the central atom, we need to distribute 3 fluorine bonds symmetrically around the central atom. Sequence looks like this, which is what he's referring to. Okay. I think it. I think we're just supposed to know that that doesn't work in boron. Okay, so we don't do a double bond there. So he only ends up with this. Okay, so that works. So in other things, we would try to put a double bond right here, but apparently that's not something we want to do. And because that would cause, if I had drawn it more carefully, see how that would cause the fluorine to have, if I did a double bond to give him a full octet, that would give this fluorine 1, 2, 3, 4, 5, 6, and then we have a double bond 7, 8, 9, 10, and then he'd have 10 in his octet, and that wouldn't work either. So we would be caught. And if BF3 never formed, we would suspect it had something to do with the octets, but apparently it does form, and so boron violates on that. Okay? I'm going to leave it to you guys to do example 510 if y'all want to work through that. Okay, so actually, I take it back. Let's look really fast at one part of 510 because this has a charge on it. Okay, so if we look over at carbon, it's got 1, 2, 3, 4. And then oxygen has 6 apiece and 3. That's 18 equals 22. All right, well, we've got this 2 minus. So what does that mean? We've got 2 additional. So we've got to have 24 total. And then once we have that, now we just work it like a normal deal. So we'd say C, O, O, and O. And then what do? We got to get rid of 24. So let's start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay. All right, so now let's move him over to make a double bond, and we'll redraw that as C, O, that's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so we've got octet, got an octet, got an octet, and got an octet. Okay, so now everybody's happy, so now we replace those, and we give them C, O, O, O. But because don't forget about this, we have to put that 2 minus here. Okay, so that's how we end up with what he's got right here. Okay, and again, see that the transition from here to here, what's happened? They spread out to get as far away from one another as they can. We'll get more into that, but just note that, be aware of that, be thinking about it so it's not a surprise. Okay? And note, what does he talk about here? Resonance structures. Okay? They're resonance structures. Double bonds here versus there. He picked at the top, I picked at the side. It doesn't matter. Okay? All right, and you guys can work those other 2 if you've got time. Okay. Exceptions to the octet rule. Okay. Boron is not the only element that does this, but it's the most common example. Okay, so you need to note that boron is the most common example of exceptions to the octet rule. Okay. Okay. Interestingly, because they're in the same group, aluminum does it too. And they minimize energy, which is the reason they break it. Okay. Looking here at NO, nitric oxide. Note that. The NO molecule is an example of a chemical species known as a free radical. I listened to a whole podcast on this just the other day. They're extremely reactive. Okay? So we need to, that's some vocabulary to be aware of. So what is it? Free radical is any atom, molecular ion that has a lone, unpaired electron. Okay? You can go through the math here to figure out why this does have that. Okay? We're just running a little bit short on time here, and you guys need to be practicing these Lewis structures without having to worry about so much of this. So we'll come back and maybe cover this a little bit more once we get Lewis structures in our belt here. Okay. More than an octet, so this is less than an octet. Boron does it with only 6. We have more than an octet, and so we've got, what do we got? We've got a decat, a 10 left. 10 electrons right there. Okay? Right? And note that this diagram, you get it this way because it resembles the way the molecule looks in 3 dimensions. Okay? And we're going to talk a lot more about that in the next chapter. Okay? Excellent. Resonance structures. So we mentioned that these are the kind of the back and forth, and they can't make up their mind. Okay? They thought that molecules exhibit a sort of resonance where the structures would switch back and forth from one structure to the other. Okay? Experiments, no idea what kind, have shown that molecules don't switch. The structure is said to be delocalized. Okay? And so how are they representing that? These dashed lines, okay? So that means like a 1.5 bond. It's not a single bond and it's not a double bond. It's a 1.5 bond. They're both 1.5 bonds. Okay? And so you see that right here as well. Except in this case, this is a 1 1/3 bond. So we've got 1, 2, 3, 4 bonds that are spread out over 3. And we've got 4 bonds over 3, branches or whatever you want to call them. So that each of those is a 4/3 bond. Okay? So it's that double bond gets spread out over however many other bonds there are. Okay? The most famous resonance structure is the benzene ring, and benzene is the C6H6. So what does that look like? We know the C's are in the middle because they always are, and they actually form a ring. Okay? And the H6, as you might imagine, is symmetrical. But the electrons don't work out right. Okay? And I wish we just had a million years, we could go through them all, okay? So what it ends up looking like is this, with these alternating double bonds. So the electrons don't work out one way or the other. Okay, so they end up with alternate double bonds. Well, how does it decide between this guy and that guy? Okay? And you'd think it maybe doesn't matter, oh, they're all H's, they're all C's, but guess what? If you pull this off, if you pull that off and maybe put something that, I don't know, let's say you put an OH right here. Okay? Now all of a sudden it doesn't look so symmetrical anymore. Okay? Things aren't the same. So anyway, so what happens is these extra bonds sort of get smeared out on this whole central set of bonds until you get this right here. Sorry. You get these half bonds, okay? You got 2, 4, 6, 7, 8, 9 spread out over 6. Okay, so you have a what? A 3 half bond, 1.5 bonds. which is then simplified to this, which is then simplified to this, okay? And then we're off into organic chemistry, okay? So we don't have to fool with that. Just to show you guys that these resonance structures can be a little bit weird, a little bit counterintuitive, and it took years and years and years for people to figure out. He actually had a dream that gave him, and I think he mentions it in here, about the snake eating its tail. Maybe he doesn't, but yeah, here it is. Came to him in a daydream and a vision. So he was so like worried about it, he never could figure it out. Then his subconscious had sort of been working on it this whole time, and it came to him. All right, so then we've got two models. Ball and stick model, which is basically just a glorified version of what we were doing. And then a space filling model. We don't actually have like, lines between them if we were able to zoom in and see. It's actually a lot more like this, although obviously there are clouds and they have fuzzy edges because of what we talked about, the probabilities and all that stuff. Okay? But that is, that's that. All right? So there's lots of practice to be done on these. There is lots more to talk about on the naming. And so I want you guys to just go through 5.3.9 and pull out your rules there. I'm working on a rule list for y'all on how to name stuff, just because we're not going to let that go, just like I won't let the converting to moles go. We're just going to keep talking about it so that when you leave chemistry, you get this really deep, practiced knowledge of how to name, how to do conversions, how to do Lewis dot diagrams. It's not going away either. Okay, so you're not just going to make it through this quiz or through this test and forget about it. Okay, you're going to have to know it because it's a basic part of knowing chemistry and a basic part of being scientifically literate. So binary covalent compounds, very quickly. Second element has the suffix "ide." Then they have both elements have the name, have a prefix, except for one, they don't bother with it. Okay, so sulfur dioxide, 2 O's, and it's mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Okay, you need to know all these. So if you're just kind of bored this weekend, go ahead and start memorizing these. Shouldn't be too hard. Tricycles have 3. Tetra, that's a little bit harder because we don't have a lot of words of that in there. Tetra's 4. Pentagon, 5-sided. Hexagon, 6-sided. Hepta, 7, 8, 9, and 10. Okay, so probably 2 of those you need to really memorize. The other ones you should be a little bit familiar with and be able to kind of work out, some familiarity with it pretty easily. Okay. Very quickly, and then I'll be done. Why do we need to have these? Why do we have to have them on the ionic ones? Okay. Well, we didn't have to have them on the ionic ones because those were done with atoms that only took one kind of oxidation state. Okay. They only were a +1 or a -1. Okay. And when they were an unknown or had multiple, they were multivalent. Okay? When they were that, we had to label them as such. Iron 2 oxide or iron 3 oxide. Those are both compounds. Okay? Well, here we've got things that might bond 12 different ways, and so it's not very practical to use those numbers in the names themselves. It's better just to use these prefixes, and that way you're just going ahead and saying it. Okay? Phosphorus trichloride. 1 phosphorus, 3 chlorines. Boom. Dinitrogen tetroxide. Okay? For nitrogen and oxygen, you have NO, NO2, NO3, N2O4. You've got all sorts of things. So you need to be able to discern between these in a way that is easily figured out for somebody who's reading words and needs to be able to write one of these. Okay? All right, good deal. We will pick up with energy and covalent bonds on Thursday, and then physical properties, and then electronegativity, polarity, and bond character. I think this is going to be a very interesting little thing, a little discussion right there. And then we'll have the nature of the bond, and then that'll pretty much take us through. You'll probably have some Lewis structure practice on Thursday, but I have to get that together tomorrow, and I have not done that yet. So, all right, guys, I will talk to you Thursday. Thanks.